to record. Okay. Where are we? The regular representation just moves everybody around. And so there's nobody on the diagonal. So the regular representation is 0 unless you are the identity element. If you are the identity element, then the regular representation doesn't move anybody at all, and you just get the size of G, right, which is the dimension of the space L2G. In general, for any character, chi, so this is facts. Fact 1, fact 2, for any GW, for any representation GW, chi of the identity can't move anybody. It doesn't change any of the functions in W. So what's the trace of that? It would be G if the dimension of W were all of G, right? This space has dimension G, but if I just have some arbitrary finite dimensional representation, exactly, it's the dimension of W. Okay, and I think this is where we stopped. So I have to prove two things for you. My claim is that the number, so given some irreducible GW, the multiplicity with which this particular representation, with which pi occurs in the decomposition of the regular representation L2G, is equal to the multiplicity, this multiplicity with which pi occurs. In other words, when you decompose L2 of G into irreducibles, you might get the same irreducible more than once. And what is the multiplicity with which it occurs? It's exactly the dimension of the representation. So this one-dimensional trivial representation, the constant function, occurs with multiplicity 1. There's nothing else that is equivalent to the constant function that will occur in the decomposition of L2G. Right? We proved this orthogonality. So anything equivalent to the constant function is not going to be orthogonal to the constant function. Why is this proof? Why is this true? Let's see a proof. Why is this true? Given an irreducible, so why is this true? Chi of the regular representation. So the regular representation, if you're thinking of the regular representation, pi GV, the regular representation is some for any element of G is some big matrix which decomposes. So this L2V V decomposes as irreducible W1, W2, and we have these orthogonal direct products. So W1 comes here, and there's some copies of things equivalent to W1. Let's write it as W1 to the E1, W2 to the E2, and WK to the EK. So W1, the representation W1 occurs with multiplicity E1. W2, so this will be W1, there's some number of W1s, then there's some number of W2s, and finally some number of WKs. Okay, these are distinct irreducibles.
We didn't put E1 representation already.
E1?
Yeah, E1 was like some.
Oh, yeah, okay. F1, L1, J1. Give me a letter. J, J1, J2, JK. Okay. So yeah, G. That's even worse. Yeah. So the point is, bless you. Whenever you have a character of V, you're taking the trace. Well, isn't that just the sum of the traces of the pieces? So this is a sum of chi W J. I can't use J. I can't use K. I. Okay, W I times Ji. Right, because that's how often it occurs as I goes from 1 to K. So I get the representation W1 occurring Ji times. This is what I'm interested in. I'm interested in this number. How often does W1 occur? So you see that when you take the trace, you get whatever Wi gives as the trace, you get that number Ji times. that make sense? Okay, and now we're almost done. Hi. And now we're almost done because the inner product of so let's compute this in two ways. Let's compute the character of this particular W. I don't know which one it is. It's one of the W's, one of the W's, inner product with chi v. Okay. On one hand, I'll expand this and use the orthogonality of characters. So let's just write it out. It's a sum as I goes from 1 to k, ji, and then the inner product of chi w with chi wi. And you remember what these character inner products are. By definition, let me just write out the definition. This is 1 over the size of g, and then a sum over g and g of chi of w of g times chi v of g bar. It's just these are now functions on g, so we have a nice, I mean, this is the L2 inner product on these functions. So what happens when we look here? By orthogonality of characters, we get a 1 when exactly for the I for which w is equivalent to wi, and 0 otherwise. So this exactly picks off ji, the multiplicity. J of w, the multiplicity with which w occurs. What happens here? Well, we know what this character is exactly. This character is size of g or 0. So it's 0 on everything except the identity element. The only thing that contributes is the identity element. And what does it contribute? Here it contributes a factor of g. Here it contributes the dimension of w. Okay, so that's why the dimension is the multiplicity. These two things are equal. Okay, so that was claim 1. Claim 2 was this is sort of one of my favorite theorems in representation theory. Although it's not going to be very useful for us for the kinds of representation we're going to be thinking about because none of them are finite dimensional. But it's a great little theorem. If you take again, write the regular representation V as W1 to the J1 direct sum WK to the JK with the WI distinct inequivalent, non-isomorphic irreducible representations, then the size of G is equal to the sum of the JI's squared as I goes from 1 to K. And of course, the JI's we know are the dimensions of the pieces. So this is a sum as I goes from 1 to K of the dimensions of these subspaces squared. Okay, and this is also a very simple proof, which is to take the inner product of chi with itself. If I take chi v, take the regular representation inner product with itself, on one hand, I get 1 over g. On one hand, I get 1 over g. Nothing contributes except the identity element. The identity element contributes a g on each of these factors. So this is g squared. On the other hand, if I decompose one of these, say, so it's a sum as I goes from 1 to k of ji and then the inner product of chi wi with chi v, writing chi v as a sum, just writing chi v as a sum of ji chi wi, and using the linearity of this inner product. Okay, and we just worked out what this is. It's ji. This is ji by the computation. And this is the dimension of the regular representation. Yes.
And with that, because you have the direct
Yes, yes, that's a great way of looking at it. Once you know this fact, yes. Once you know that the multiplicity is the dimension, well, then there's whatever the dimension of W1 is, there's that many W1s, so it's that dimension squared, summed up exactly. Yeah, you can see it from this picture, maybe more easily than this calculation. Some people prefer pictures, some people prefer to calculation. Now we've done both, so no one's happy. Okay, so once we've done this, now let's go back to our favorite group, this this S3. We found one irreducible subspace. So far, so back to L2 of G, where G is S3, we found this is V. V decomposes as W1, direct sum, well, the rest, W1 perp. And the size of G is 6. And so 6 is going to be a sum of squares. This is a sum of some Ji squared. I know that I have this constant times E1, where E1 is the trivial thing, a constant function. How am I going to write 6 as a sum of squares? I already have 1 squared, and then I have to write it out as a sum of other squares. Well, it could be 1 plus 1 plus 1 plus 1 plus 1. It could be all one-dimensional representations. But if it was all one-dimensional representations, then this group would have to be abelian. So it's not going to be all ones. And if I put even a single 2 here, that comes with a multiplicity of 2. So that's 2 squared is 4. So in fact, there has to be one more one-dimensional representation and then 2 equivalent two-dimensional representations to make up. So that's what we're looking for. We're looking for a basis that'll consist of one more one-dimensional subspace and then 2 two-dimensional subspaces. Okay, and then we're almost done with our crash course excursion into representation theory. So how are we going to find this? So again, let's recall what the action is. What does A do to all of our elements? E, A squared, B, AB, A squared, B. A maps this, A maps this. So in other words, right multiplication by A maps this to A squared times A is E. B times A is A squared B. AB times A, now I have to do this off to the side. AB times A, this is A squared B, that's just B. And then this one has no other choice but to be AB. That's a permutation. So what permutation is this? If I started with EA, A squared, B, AB, A squared B, the permutation takes E to A, so that's 0, 1, and then all zeros. A to A squared, that's 0, 0, 1, and A squared to E, that's 1, 0, 0. We sort of have these two 3x3 subblocks. They seem to be staying together. And then B goes to A squared B, that's over here. AB goes to B, that's over here, and then I have no choice but to put A squared getting sent to AB. And once we know what happens on the generators, we know what happens to everybody. What does B look like? B will map the same thing, EA, A squared, B, AB, AB squared, A squared B, thank you very much. AB squared is A squared B. This is even easier. I'm multiplying on the right by B, so I get B, AB, A squared B, and B squared is 1, so I get E, A squared. So this is, so you can really see hopefully your mind is mapping the geometry of all the various triangles and their configurations. A squared B. Okay, so what has happened? E has gone to B, A has gone to AB, and A squared has gone to A squared B, whereas B has gone to E, and then A squared. Okay, so we want, so obviously if you add everybody up and then you apply these transformations, you're invariant. What's something else that's going to be invariant? Oh, and what's the character? Well, the character, okay. And what's the character of this representation? So let's call this pi 1. So there's pi 1 acting on this sum. It's a one-dimensional representation. So it takes values on the characters. What value does it take on E? Pi 1 sends E the class of A or the class of B. I'm using pi. Well, pi is the character because it's a one-dimensional representation, and the trace of a one-dimensional representation is just the value. It's a 1-by-1 matrix in this case. So I take the element E1 and I move it by E. It doesn't do anything. So pi is the matrix of where it sends E1. In other words, E1 is an eigenvector of all of the pi's. And the question is, what's the eigenvalue? Right? You see that pi? What is pi? Pi is just exactly this regular action on functions. And what I'm doing to the functions is I'm adding all of the indicator functions of E, A squared, B, AB, A squared, B. And so when you apply actually any element, you just get back E1. So pi doesn't do anything. Pi as a matrix, pi is the 1-by-1 matrix of the constant 1, the identity 1-by-1 matrix. And so the character just takes the value 1 everywhere. Okay, that's the trivial character. Can we think of another subspace that's orthogonal? So E2, we want something that's orthogonal to E1. That will be, we want it to be one-dimensional, so it's going to be an eigenfunction of all of these actions of pi 2, whatever pi 2 is. Joy's got one?
You put 3 ones and then 3 negative.
Beautiful. 3 1s and 3 negative 1s, because the EAA squared seem to be staying together, and the BAB A squared B seem to be switching. This is certainly orthogonal to E1. Right? I got 3 plus 1s and 3 minus 1s. That adds up to 0. And so what does pi A do to E2? So I'm going to take the E's, the EA and A squared, and I'm going to permute them. And I'm going to take the BAB A squared B and permute them. What does it do to E2? Leaves it alone. It's E2. What does pi B do to E2? Negative E2. Exactly. It switches the EAB with the BAB squared. Okay. So the character, so pi 2, what's the character table? So again, I need to know what its value is on E, on the class of A, and on the class of B. And on E, it always takes the value 1. It's a one-dimensional representation. On A, it takes the value 1. The eigenvalue is 1. On the class of B, it takes the value negative 1. So it has 1 1, 2 more 1s, and then 3 negative 1s. And that's why it's orthogonal to this E2. Great, we've peeled off another invariant subspace. It's clear that it's invariant because we mapped E2 to itself under the action of A and B, and those are the generators. So everybody keeps the vector space of E2 fixed. So now it gets interesting. Okay, so now we have this subspace W2 spanned by E2, and this is pi 2 and chi 2. So now it gets interesting. We know we need a 2-dimensional representation. So we're not going to get a vector that gets sent to itself. We'll have a vector that gets sent to its friend, but its friend gets sent back to itself. And it has to behave in this way. In this order 3 permutation way. Any suggestions? And it has to be orthogonal to E1 and E2. Joy said something last time. You want to say it again? Yeah, how about 1 omega and omega squared, and then 0, 0, 0, where omega cubed is 1. So omega is a cube root of unity. There's omega squared. So omega is, what is this, -1/2 plus root 3i over 2? So the sum of these 3 roots is going to be 0. So this is orthogonal to both E2 and E1. Bless you. What does A, let's see, what does pi 3 of A do to E3? So remember, if I had a function who was evaluating, so I'm taking 1 times E plus times the indicator function of E plus this complex number omega times the indicator function of A plus the complex number omega squared times the indicator function of A squared. And when I apply the regular representation, with multiplication, right multiplication by A, these guys get permuted. So where does it go? I get 1 times A, I get 1 times A, so I'm writing this, I'm still expanding this in the group basis. I get 1 times A, omega times A squared, and omega squared times E, and nothing over here. But isn't that just omega squared times E3? Omega squared E3. Oh, beautiful. Maybe we will have a one-dimensional subspace. Wait a second. It's not enough to see what pi of A does. We also have to know what pi of B does. Pi 3 of B acting on E3. What happens to E1? What happens to E? 1 times the indicator function of E becomes the indicator function when multiplied by B, the indicator function of B. So this becomes the indicator function of B, and then omega times the indicator function of AB, and omega squared times the indicator function of A squared B. But that's not, this vector is not in the span of E3. So we better have a new vector E4, which is 0, 0, 0, 1 omega omega squared. It's orthogonal to E3, it's orthogonal to E2, it's orthogonal to E1. And these two guys form a subspace called W3. So W3 is generated, W3 is the space generated by E3 and E4. And now I have to check what pi does to E4. So what is pi 3a acting on E4? So remember what A does. A just moves around the E's, and it also moves around the B A squared B. So it sends B to 1 times B, it sends to 1 times A squared B. So that's 0, 0, 0, 1 times A squared B. Where does it send omega times AB? It sends omega times AB to omega times B. So there's an omega here and an omega squared there. So this is what, omega times E4?
I'm uncomfortable with them talking different heights.
You'll see in a second. Yeah, we're almost done. I need one last calculation, which is pi 4, pi 3b acting on E4. What does pi 3b do to E4? Well, B is an involution. So if it sends E3 to E4, it has to send E4 back to E3. And you can see easily that that's exactly what it does. It sends BAAB to BAB A squared B to EAAB. This is E3. So now we can write pi 3, we can write in the basis. So what does pi 3 do? Pi 3a, what does it do to the pair E3, E4? It sends it to E3, E4 multiplied by the matrix. E3 just goes to W squared times E3. That's W squared times E3 and no E4s. What does it do? What does pi A do to E4? It maps it to W E4 and no E3s. So this is the way that pi 3a is a 2 by 2 matrix. What about pi 3 of b? Pi 3 of b, how does it act on E3, E4? It's going to map by something, it takes E3 to W squared pi b. It takes E3 to E4, and it takes E4 back to E3. And now we can work out the character. So chi3 on the class of A, or on the class of B, or on the class of E takes what values? So on the identity, it always takes the value 1. Good. It's the dimension. It's not 1. It's the dimension, right? On the identity, it's just 1, 1 on the diagonal. The identity element doesn't do anything. Leaves alone E3 and leaves alone E4. So that's going to be a trace of 2. What's the trace of A? Yeah, W plus W squared is minus 1. Minus 1. And what's the trace of B? 0. And now you see the orthogonality of the characters also, because this 2 happens once, the -1 happens twice, and the 0 happens 3 times. The size of the conjugates class of B. There are 3 elements of order 2. Does that make sense? I realize, okay, we should do an entire course in representation theory. This is meant to be a little aside. So we've hopefully you see some of these things. So we've picked off so far. So now V has been decomposed into V, the regular representation, has been decomposed into a one-dimensional trivial space, plus a one-dimensional space spanned by 3 1s and 3 -1s, this vector, and a two-dimensional space spanned by E3 and E4. And now I need, this is only 4 dimensions. I need another W3, but it's W3 in the sense that it's isomorphic to W. This W3 tilde is isomorphic to W3, but it can't be the same vectors. I need to fill out the vector space. So I need to find more vectors that are orthogonal to E3 and E2 and E1 and E4 that have the same behavior. So how do I find more vectors that are orthogonal to E3 and E2 and E1? Well, E1 and E2, like in the first components, they're both the constant vector of all ones. So if I have all ones and I have this other vector and I have to be orthogonal to those 2 vectors, I know how to do that. That's the cross product. Right? So to find E5, let's take the cross product of 1, 1, 1 with 1 omega omega squared. And then what do you put here? IJK? How do you guys do this? You just put dots? Oh, at the top. I see. Well, it doesn't matter. Yeah. Oh, yeah. This is completely unrelated. Well, I think this way does work. You put them on top.
Yeah. The worst thing is change the determinant by a negative.
That's right. That's right. So if I take the I, that's the minor is W squared minus W. W squared minus W, which is some W squared minus W, it's some imaginary root-3 thing, whatever it is. Let's just leave it as W squared minus W. When I take the J, it's with a minus sign, it's W squared minus 1, so 1 minus W squared. And when I take the K part, that's W minus 1. W is omega, of course. Now, this is not the right E5. If we replace omega by omega squared, right? That will not be orthogonal to E3. So if I put 1 omega squared omega, then when I take the inner product with E3, oh, actually, that will work. Yeah, it's exactly what I was saying here. This is the wrong E5 because the way to take the inner products, this is a unitary representation. You have to take conjugates before taking inner products. So we can take E5 to be 1 omega squared omega 0, 0, 0. And when you take the inner product of E3 and E5, you see you don't multiply 1 by 1 and then add that to omega times omega squared, which would be omega cubed, which is another one, and then omega times omega squared, which is another one. That looks like 3 ones adding to not 0. It's the bar of this. So it's 1 plus omega squared bar, which is omega. So this inner product is 1 and 1 times 1 plus E3 is omega times the bar of omega squared, which is also omega, plus omega squared times the bar of omega, which is omega squared. Now this is omega plus omega squared plus 1. This is 0. So if you had taken this cross product, you have to take the conjugates to make the E5, and that will be a constant multiple, this 1 minus W multiple of 1 omega squared omega. But if you didn't think to do this, you could have done something more systematic by taking a cross product. I just wanted to make the note that you have to conjugate this cross product to get something whose inner product in this unitary L2 sense will be 0. Okay, and then E6 is clear. E6 is 0, 0, 0, 1 omega squared omega, which is orthogonal to the other E4, and it's orthogonal to E3 because they have no factors in common. It's orthogonal to E5. So we have now a very nice basis. So these two representations together make W3 tilde, which is isomorphic to W3 as a G representation, but it's just a different subspace, different vectors spanning the subspace of L2. Okay, so there are kind of two things that people like to think about. People like to think about irreducible representations just on their own right, and that's what we're going to be focusing the rest of the course on. But I, for some reason, took this detour into things that you can get out of the decomposition, decomposing L2, all of L2, L2G, is also, to me, a very important component that I think in a lot of, I don't know, when you guys learned representation theory, did you complete the decomposition all the way down to the level of the various subspaces? And let me tell you why I think that's important. Let me just give you one example. One example of the way of use of the way that 2 occurs in applications, of 2 occurring in applications, in real applications. I mean, real math applications, of course. So here's one example. And then we're back to Adele's and Dirichlet characters and all that good stuff. Here's one example. Let gamma be SL2Z. And I want to know N of T is the number of matrices A, B, C, D in gamma such that let's say the L2 norm of the matrix is bounded by T. So A squared plus B squared plus C squared plus D squared square rooted is at most T, but I don't like square roots. Okay, so if you think of SL2R, so let G be SL2R. If you think of SL2R as a ball, I'm just drawing schematically, although there's a way that you can make sense of it as a ball, the disk model of hyperbolic plane, then you can think of the origin in gamma being here, and then we have some orbit of points. So this is G, and these dots I'm thinking of as gamma, and then I'm going to look at all the ones that are inside a ball of radius T, some radius T ball. I want to count how many there are. Okay, this is the very standard kind of question that number theory tries to answer. I don't know why it's a number theory question. It should just be a geometry question, a dynamics question. And in fact, it is a question in all those things. I guess it smells of number theory, at least written this way, because SL2 is determined by AD minus BC equals 1. Any solution to this equation, to this any point on this variety over the integers corresponds to a matrix in SL2Z. That's the definition. That may seem trivial, but if I took some subgroup of SL2Z that's not a congruent subgroup, it's no longer determined just by this determinant equation. It's determined by whatever, you give me some matrices in SL2Z and give me the group generated by those matrices. I have no good way to describe what a typical element in that group is without reducing it to checking that it's a word in the generators. Okay, so this is hiding group theory, it's hiding geometry, it's hiding dynamics. So this is the kind of quick question that you might like to answer. Does that make sense?
In that picture, you took a dot and then you acted on.
I just took the identity element.
Yeah.
This is I'm not even thinking of an orbit right now. I'm just thinking literally of G as a ball. This is schematic. It's not a real picture.
And then these points are just points down.
The points are the discrete, yes, this discrete subgroup of SL2. Okay. Some of you have a picture for the quotient space, which is a good picture to have. If I draw something in the upper half plane that looks like this, maybe this is a picture for some fundamental domain D, which is a fundamental domain for G mod gamma. It's not exactly right because I'm not showing the tangent vectors, but never. If you don't know what I'm saying, just ignore it. This is the question I'm interested in. Okay, there. That's the question. How could you access this question using the ideas of decomposition of L2 of something? Well, let's make a function. Let little f. By the way, this condition that the sum of the squares of the elements is also equal to the trace of, let's call this element gamma, of gamma times gamma transpose. That's an easy, this is called the Frobenius norm. Frobenius norm. Okay, you take gamma, you multiply it by its transpose, you get an a squared plus b squared in one entry and c squared plus d squared in another entry. You take the trace, you get the sum of the four squares. Okay, so let f sub t of g, any g, we're going to make a function on SL2R. This is a function on SL2R. Let f sub t of g be the indicator function of whether this Frobenius norm, let's call this norm squared. I mean, you would want to take the square root of that to get a nicer norm. The norm of G being at most T. Okay, so this is the indicator function of a ball of radius T. So in other words, in this schematic, it's 1 here and 0 elsewhere. Okay, now this is a function from G, from SL2R to C. I mean, it only takes values 0, 1, but we have a function on this ambient Lie group, SL2R. What we want is the value of the function on Z, on SL2Z, but it's not defined on it. So we're going to do the same thing. If you remember all of our proofs of Poisson summation and Mellin transform, we're going to do exactly the same thing. We're going to automorphize little f to big F T of G will be the sum over gamma in gamma, this SL2Z subgroup, ft of gamma G. So you see how this is like a right regular representation. The G is acting on the right here. So in other words, I'm taking this ball, I keep moving this ball centered at other points, and I add those things up. Okay. Is this a function on? What is this a function on? Where does it take values? Gamma's got a lot of stuff. Yeah, gamma's an infinite group. So it certainly takes values in G. Yeah, it's invariant under gamma. If I replace G by some, if I stick in some, so ft of gamma G for any gamma in gamma will be ft of G. So in fact, it takes values on the quotient. It's invariant. We've automorphized it. We made it invariant under the group. Some people like to write this as the class of G, or the class of G. Yeah, well, yeah, that's fine. Or the coset of G. So it takes values in cosets, gamma cosets. Right? It takes the same value on any coset. Yeah, so you sort of are decomposing all of G into gamma cosets, which this is a fundamental domain for. Whatever this, if this picture has meaning to you, great. If not, it's just a schematic. We're not going to do anything serious with this. I just want to illustrate somehow that the simple ideas in representation that we've been talking about actually have a very close correspondence to real questions that people care about using techniques that you're familiar with, just in a slightly different language or point of view or something. Okay, so we have this function. So we have a nice function. So we have ft. This ft is in L2 of G mod gamma. Yeah, with respect to what? Well, with respect to Haar measure, which I haven't described, this is some kind of Haar measure, invariant Haar measure on G that descends to the quotient G mod gamma. Let me not describe it. It's just some Haar measure under which it turns out that SL2Z is a lattice in G, which means fact is that the volume of G mod gamma is finite, even though it's not compact. Pi over 3, correct. Depending on your normalization. Yeah. Okay. And so if we have this nice function, well, let's decompose it into irreducibles. So to access, why do we care about this function? What does this function have to do with our original problem of counting? Teddy, I lost you. What is the value of this function, capital F, at the identity, at the origin? So if I put the identity here, it's just F sub t of gamma. F sub t is the indicator function of whether you're not in the ball of order t, of radius t. So it exactly counts how many of these points are inside the ball. This is exactly our counting problem. Okay, so I'm going to try to understand the function f, which means I'm going to try to understand the count by understanding the function. And what I'm going to do with the function is decompose it projected onto the various, if I can decompose, so we'll want to decompose this V into irreducibles. Or maybe not all the way down to irreducibles. Maybe just pick off some nice invariant subspaces. Or just some nice invariant subspaces. And project and study the projection of Ft onto those subspaces, to the subspaces. That should tell us something about how many points there are in SL2Z. In practice, this is exactly how a lot of the counting theorems that then get put into sieves or circle method or like any of these other applications. This is the machinery that's underlying that. Yeah. Okay. Can we think of any invariant subspace? There's some vector that's just jumping out at us. It wants to be invariant under the group action. It's a complicated space. The group is going to do all kinds of crazy things to vectors. There's always one guy. Well, not always, actually, but the fact that the volume is finite means that there's, what is it? I think you're right. Whatever you were starting to say. The constant function. The constant function is the only guy I can think of. The constant function, the function that just takes the value 1 on everywhere. You'll see in a second. Yeah. So V is the constant function of all just being 1 on the quotient. That is in L2. The constant function is square integral exactly because when you try to square integrate it, you get the volume, and the volume is finite. So yes, that's square integrable. So the constant function is square integrable, and then let's just say V per. Okay. So this FT now you have to start being you have to do some not functional analysis, but some analysis, because I want to evaluate this function at a point. To evaluate a function at a point, this is an L2. L2 functions don't have values at points. They're up to equivalence. So you have to do some kind of smoothing and unsmoothing. And anyway, this function isn't smooth because it's a sharp cutoff. There are all kinds of issues with what I'm about to say, but let's just go with it. What's that? Really? Yeah, you're surprised. Because I'm always running into issues. Ft, when I project it onto the constant function, what does that mean? It means take the inner product. This is a one-dimensional space. So I'll take the inner product of Ft against 1, and I'll multiply that by the constant function. You will, not of 1, but of Ft. 1 is a nice smooth, so there is a dense subspace of smooth functions in L2 for which you can evaluate. And then you have to show that this decomposition, if we take a full decomposition, converges on compacta if it's an infinite sum, or if you just leave it as the space orthogonal to the constant function. Maybe you can say something about this space, like it's tempered, its matrix coefficients are in L2, whatever all those things mean. But let's say we write Ft of G as the projection onto the constant function, and then the orthogonal part. Okay, so V is some massive infinite dimensional space. We found one direction, we found one subspace, and we have our part. So this is the span of the constant function, and then we have our function that we're interested in, f sub t, in this space, and we're going to just work out what the projection is and the orthogonal complement. Ft per is somewhere here. Okay. Now 1 evaluates on any function 1 on any element of the group. It evaluates to 1. What is this inner product? Let's work out this inner product. Okay, what's the inner product? The inner product, this is the inner product in the space L2 of G mod gamma. So it's an integral over G mod gamma of f of t of G times the constant function 1 bar, thank you. Yes, of course, bar, with the Haar measure d mu of G. And maybe we want to normalize this to be a probability measure. So maybe we normalize, instead of this pi over 3 factor, we'll just normalize by dividing by the volume. Now the Haar measure is a probability measure. Okay. So far, so good. What was capital F? Capital F was defined as the averaging of little f over the group. Maybe this is going to start to seem familiar. I'm going to take this volume of the quotient. Now, once I start opening the automorphy, I actually have to fix a fundamental domain. So fix a domain, fix fundamental domain D. So I have this integral over my fixed fundamental domain, a domain for G mod gamma. And then F, capital F, is a sum of little f at gamma G summed over gamma and gamma times 1 dg. It's the same thing that we've done 1,000 times in this application. Looks like this. I have this 1 over volume. Who's going to tell me I got 2 sums? I got to flip them. Oh yeah, okay. Joy moved, and so okay. I don't know where to point anymore. Right. I've got 2 sums. I'm going to flip them. Everything is convergent, absolutely convergent. There's no question about positivity, about non-positivity. F sub t of gamma G dg. Then what will I do to this? I'll make a change of variables. How many times have we done this calculation? I'll make a change of variables. So instead of f of t of G, let's say H is equal to gamma G, dg is dH, that's invariant. And instead of running over D, now I have to run over gamma D because of Haar measure, invariant Haar measure. Now there's no more gamma anywhere here. When you add up, when you take your fundamental domain, D, and you start translating it by gamma, you get a tiling of the whole space. So this is 1 over volume times the integral over all of G. This tiles all of G, ft of H dH. Have I completely lost all of you? Some of you. What was ft? Remember our picture of g? This is g. It's the indicator function of a ball. So this is 1 over the volume of g mod gamma times the volume of a ball of size t in g. This is the ball of size t in g. Ball of radius t in g. Okay, so if we put this all together,
So you have to like split the order in order to do this change of variance.
that's right, which means I have to take a fixed fundamental domain for the quotient
Right.
once I open the automorphized function into its sum of constituents.
And it's just for this change of variance. Then after that, you do these adding up and then you can have to do
Right,
this full sum.
right. So, but look at what we've done. We've said this counting function, if you believe that the constant function is sort of the main term, that this so ft at e, which on one hand is a sum of ft of gamma times e summed over gamma and gamma, which is actually the counting, exactly the count that we're interested in. On the other hand, is equal to this integral. Well, there's this normalizing factor 1 over volume, and this integral over ft of h dh over all of g, plus, well, an orthogonal part that we haven't discussed, that one would have to deal with to get an actual asymptotic. This is Poisson summation. It's exactly what we do with Poisson summation. This is an abelian Poisson summation. An abelian Poisson summation. We took a function, we automorphized it. We have a group here. Here, what we get, if we really expand this all the way out, it's the irreducible, it's the projection of ft onto the irreducible component. That's the spectrum. That's the spectral side of the trace form. So just like we saw, just like when we had for real valued functions, f of n summed over n in z is equal to, I always insist on saying f hat of m in z. It's these m's are the irreducible subspaces in the full decomposition of L2. This is the decomposition of L2 of R mod Z. Well, we had a special value for F because we had a particular counting application in mind. But actually, this is a completely general statement.
Oh, I see.
That has to be made precise because I'm evaluating an L2 function per point, and it's not smooth and so on. There's all kinds of issues. But what was, by the way, this, if I take out f hat of 0, sort of the main term, plus a sum over the other terms, m not equal to 0, f hat of n. What is f hat of 0? The Fourier transform with no spin. It's just the total mass. This is f hat of 0. And that's the main term. It gives you the volume of the ball. The number of points that you get in the discrete group is just the volume of the ball divided by the covolume.
So
isn't that nice?
This other term
Yes, this term will be lower order. You have to prove that. There's a lot more that we would have to put together to prove that this is lower order.
is it much lower order?
In smooth form, this will grow like t squared. You can work out this volume, and it's like t squared. And in smooth form, which I haven't explained how you do that, you can get this to be square root of the main term. It's exactly, it's the Gauss counting, except on z, instead of z squared, we're doing it in SL2z. Gauss you can do with your hands. This you can also do with your bare hands using completely different methods, but I'm trying to highlight. But you can't do with your bare hands when you don't have SL2Z. If you have some group that's really defined by matrices and not by that's not all the integer points on some variety, then there is no other method for general groups that works in this generality. So this decomposition is really something very, very robust. For SL2Z, because you can try to play all kinds of tricks with Klosterman sums, actually you can get this counting statement without thinking about spectral theory. But it's very difficult and tedious, and people have done it.
Wait, so you're saying main term is t squared.
Yes, the constant function is always supposed to at least contribute the main term. And the issue is how to show that the error is has
error
levels.
term t.
That's right. When you do this again in smooth form, you take the inner product of this ft with some bump function, then here you'll get a big O of t, because the rest of the spectrum is tempting for SL2Z. Otherwise, you're dealing with the Ramanujan, conjecture and Selberg one-quarter conjecture. Okay, I think I have gone way far out on a limb from what I had intended to talk about, which was Dirichlet characters. But hopefully this I don't know, will motivate something about Dirichlet. Let's go back to Dirichlet. Okay, back to Dirichlet characters, and then we'll go all the way back to the Adels. Obviously not this time. Back to Dirichlet characters. Well, so what will turn out is that the decomposition of L2 of the Adels, the Edels modulo the rationals, will be basically parametrized by Dirichlet characters. So the only irreducible, it's already abelian, it's GL1 of the, yes. When we take the decomposition of the Edels modulo Q cross, modulo the invertible rationals, the Edel group acts on this and decomposes it into the irreducibles. Now this is abelian, so we're only going to have one-dimensional subspaces. And so those will be basically parametrized by Dirichlet characters. That's what we're building up to. But first, I just want to remind you about the classical theory of Dirichlet characters and how that whole story works and why you get these Dirichlet L functions. I want to see them classically, and then we'll see them adelically. Okay, so if the last two lectures were a complete blur and if you liked it, there's more of that to come. If you hated it, we're done with that for now. And don't worry about it until it comes back. Okay, so Dirichlet characters. So now our group, we're back to the setting of a finite group. Our group is Z mod NZ cross, the multiplicative group. It's abelian, so it only has one-dimensional representation, so we can speak of the characters. By the way, I forgot to say, notice that characters in general do not have to be non-zero. It's only when we have one-dimensional representations, they have to be invertible matrices. One by one invertible matrices are non-zero. Okay, so one-dimensional representations have non-zero characters, but higher dimensions certainly can have zeros. So just to bring home that point. So chi is a character, is a map from G to C cross in this case. And we extend that character. You remember that we talked about Dirichlet characters. It was a couple of lectures ago. So hopefully you remember what these things look like. We worked out the table for Z mod 12 or something. We're going to extend a character. So lift a character chi from Z mod n cross to just Z mod n by setting it to be 0. Set chi of m equals 0 if n and m are not coprime. I want to do the classical Poisson summation twisted by Dirichlet characters. Okay, so that's the first lift. Then we lift chi to z, just take the pre-image of z mod n. Okay, so now we have a function on the integers, periodic mod n. It takes the value 0 if m and n are not coprime. Otherwise, it takes whatever value the character gave it. So far, so good. And now the next thing that I want is a twisted Poisson summation formula. It's a twisted Poisson summation formula. Of the type, I sum f on the integers. I have my favorite test function f. That's just the left side of the Poisson summation formula. I'm going to multiply this by a Dirichlet character. I want to know what happens on the other side. So I take the value of my function like a Gaussian or something, but I'm going to multiply it by zeros, ones, minus ones, maybe roots of unity. And when it's spun around like this, do I get something reasonable on the other side? Now I would immediately get such a thing just applying the regular Poisson summation formula if I could extend chi to a real value function. Right. So our last thing to do, extend chi to a function on R. Right now it's a function just on the integers. I claim it's actually not that hard. It's actually really simple to extend it to a real valued function in which I just take the Fourier transform of the product of these things, or maybe something even better in the standard Poisson summation. Okay, so I have an integer valued function. How am I going to make a real valued function out of it? It seems like, you know, I have the values on the integers. It's this or this or this or some complex number which I can't draw. And now I'm going to interpolate in some nice way. Interpolate. Yeah. No. Yeah. Convexity is I guess, yeah. What?
Yeah.
That's right. Yeah.
How do you make it?
From factorial. Right. Okay, so here's what we're going to do. Can I do this in 5 minutes? I think I can. I'm rushing, aren't I? I should go slower. What's that? That somebody said something. No. Okay, so I have another space that I want to decompose into irreducibles. I'm a one-trick pony. Give me a space. I want to decompose it. On the space L2 of Z mod N Z, we have a very nice decomposition. This decomposes into a direct sum of one-dimensional irreducible subspaces spanned by E sub M, as M ranges mod N, where E sub M of A is E to the 2 pi I AM over N. Now I'm saying something completely trivial, that the roots of unity, the nth roots of unity, give you characters on the additive group mod N. Right? This is just a finite dimensional space. Now we lifted chi. Chi is a function that's in L2 of Z mod N. When we lifted it to Z mod N, we had a function that was in L2 Z mod N. So we can decompose chi with respect to the spaces, which is just finite Fourier transform. Okay, so decompose pi, decompose chi. So chi hat of A, say, will be a sum over M mod N. Chi of M, E to the 2 pi I AM over capital N. And I like to normalize this with a 1 over root N. As you'll see in a second, that's a good normalization. Just so that the Fourier transform and its inverse look the same. Okay. In fact, this is completely general. This has nothing to do with chi. Decompose any F for any F. So let me make this an exercise, because it's really just orthogonality of the nth roots of unity. For any F in L2 of Z mod N, you define F hat in this way. And then if you take, so let me write it again. F hat of A is the sum M mod N. F of A is of A takes values in Z mod N. A is F of M. M takes values in Z mod N. E to the 2 pi I AM over N. And with this normalization, M. Thanks. Set F to be this, and then the exercise is then if I take the F hat of A's, I multiply them by the conjugate character, E to the 2 pi I AM over N, and I sum over A mod N, and I divide by the same normalizing factor root N. This will recover F, the original function, at M. Okay, all I'm doing is I'm taking my function in here and projecting it onto these spaces. That's what this projection is. I guess technically, if you want to think about it as a projection with a Hermitian projection, this should be a minus sign, but I always put the plus sign for my Fourier transform, minus sign for my inverse Fourier transform. And then when you have the projections, you add up all the projections, you get back to the original vector. That's all it means for this to be a basis. It's an orthonormal. These functions form a nice orthonormal basis for this space, on which the group Z mod n acts, nicely. So far, so good. Okay, so what we're going to do next time, since we're out of time, is we're going to study these Fourier transforms and recover chi. Well, I can tell you now already, chi of m is by this formula, e to the 1 over root n, a sum over a mod n of chi hat of a times e to the minus 2 pi I a m over n. And the only observation we want to make here, we want to make a couple of observations. We have to understand this Fourier transform a little bit better. But this function, as it stands, can take real valued m. It's a finite sum with whatever these Fourier transforms are, and there's nothing stopping me from taking this m to be real value. And that will be my extension of chi to the real numbers. Or complex, or p-adic, if you want to be really, I mean, okay, n has to be a prime power or something.
And so this is the coincidence. No, you can't consider the complex. Because when you multiply by I,
well, this formula makes sense for m, a complex number. It doesn't mean, so this gives me a way of creating a complex value. It's just the exponential function. Even when m is complex, I agree, I multiply by I, so this does not have absolute value 1. So what? It's still the exponential. The exponential function is defined on all complex numbers. So this formula, yes, or C, but I'm not even going to write or C. That's just too much. Come on. Poor Chi has been extended so far already. Let him be. Good. We are back down to earth. Forget about the representation theory. We'll do this chi, and then we'll go back to the Adels and get back on track with what I was supposed to be talking about before I took this detour. But I hope the detour will have been worth it when we see at least some semblance of these ideas later.